It's almost absurd how casually we interact with temperature today.
Oh, absolutely.
Like you wake up, you roll over, and you check the weather app on your phone to see exactly how many degrees it is outside before you even, decide what shirt to wear.
Yeah, or think about going to a clinic, right? A nurse points a little plastic scanner at your forehead, it beeps, and instantly, down to a decimal point, you know if a fever is breaking.
Exactly. It just feels like reading the time on a clock. Yeah. But if you rewind for most of human history, like up until about 400 years ago, that reality simply did not exist.
It really didn't. There is absolutely no way to put a number on heat.
Right. Hot and cold were entirely subjective human feelings. It was just, I feel warm today, or this fire seems hotter than the one we built yesterday. That was the absolute limit of our understanding.
Which is a profound limitation, really, because if you cannot quantify a force, you can't truly control it. You can't replicate it or communicate it accurately across time and space. You are just trapped in subjectivity.
And that massive paradigm shift, going from merely feeling heat to mathematically measuring it, is the mission of our deep dive today. Yeah. We are pulling from an incredible curriculum excerpt from the learning platform Befried. It's titled Measuring Temperature and the History of Thermometers.
It's a great piece.
Yeah, and we are going to explore how humanity managed to take something completely invisible, something that was experienced entirely as a physical sensation, and basically turn it into precise, harnessable facts.
The source material actually captures this transition perfectly. There is a quote early on that really sets the stakes for this entire historical journey.
Oh, right. The one about being at the mercy of it.
Exactly. It states, "We went from being at the mercy of the heat to being able to harness it, measure it, and use it to build our world. It represents a transition from a subjective feeling to a measurable fact."
I just find that phrasing so compelling. We were at the mercy of it.
Yeah, it isn't just a timeline of glass tubes and liquids, It is the story of humanity's quest to isolate and measure the invisible mechanics of nature.
Okay, let's unpack this. Because before we could measure the extreme heat of the cosmos, or, even reliably measure the temperature of a baking oven, we had to start with something incredibly basic.
Very basic.
We had to start with trapped air.
Right, so we have to travel back to the late 1500s. We meet Galileo Galilei, who was grappling with this exact problem of invisible heat.
Yeah.
And the source notes that Galileo invented an instrument called a thermoscope. Notice it is not a thermometer, but a thermoscope.
Right, and the mechanics of this early device are brilliantly simple, but also, well, as we find out, deeply flawed.
Oh, very flawed.
The Befried text explains that Galileo's thermoscope was essentially a glass bulb with a long, thin tube extending downward. And he would invert this tube into a basin of water.
Mm-hmm.
So when you place your warm hands on the glass bulb at the top, the heat from your skin transfers to the air trapped inside. As that air warms up, the gas particles gain kinetic energy, they expand, and that expansion physically pushes the water level down the tube.
Yeah.
Take your hands away, the air cools and contracts, and the water level rises back up.
It's a beautiful visualization. Galileo is effectively giving heat a physical body that you can watch move up and down in real time.
Right, like a magic trick.
For a society that had only ever felt heat, watching it perform physical work inside a glass tube was a total revelation.
But the source points out two glaring issues with this setup. First, the thermoscope didn't even have a scale.
Right, no numbers.
Yeah, there were no tick marks on the glass. It was literally just a floating water line. You couldn't say it's a level 5 today. You just had to look at it and guess, well, the water looks a bit higher than it did yesterday morning.
Which means you are still essentially trapped in a degree of subjectivity. You have a tool that reacts to heat, but you still lack numbers. You have no universal language to record the data.
Exactly. But the second issue is the real deal breaker. Like, I want you to imagine being a doctor in the 16th century. You are sitting at the bedside, trying to figure out if your patient's life-threatening fever is finally breaking. You are relying on this thermoscope.
Yeah.
You watch the water line carefully. But wait, if Galileo is supposed to be this brilliant scientific pioneer, how did he miss the fact that a cloudy day completely ruined his entire instrument?
Yeah, that is a huge problem.
The source explains that this thermoscope changed every time the air pressure shifted. So if a thunderstorm rolled into town, the atmospheric pressure dropped, the air in the tube reacted, and the water line shifted dramatically.
Unpredictably, too.
Right. Your patient suddenly looked sicker or magically cured simply because a weather front moved in. Like, how could a genius overlook that?
Well, it wasn't necessarily an oversight. It was a limitation of the scientific knowledge of the era.
Oh, really?
Yeah, at that time, the concept of atmospheric pressure, the idea that the ocean of air above our heads actually has weight and pushes down on us, was not fully understood.
Oh, I see.
That realization came slightly later with scientists like Torricelli, but you are hitting on the exact reason why this was such a frustrating era.
It must have been maddening.
The source actually addresses this in a frequently asked question about why Galileo's thermoscope gave such inconsistent readings. Atmospheric pressure acts like an invisible hand pressing down on the water in the basin.
Oh, that makes sense.
So if you have an open system, which Galileo's was, you aren't just measuring temperature, you are measuring temperature fatally intertwined with barometric pressure.
It's like trying to accurately weigh yourself on a bathroom scale while someone else randomly pushes their foot down on the edge of it.
Exactly.
The data is hopelessly corrupted by an outside force.
That is a perfect way to visualize it, and this raises an important question. How do you separate the measurement of heat from the interference of the atmosphere?
Right, because otherwise it's useless.
Because until you can isolate the heat, your instrument is just a glorified weather vane. This absolute necessity drove what the source accurately describes as the quest for isolation.
The quest for isolation. It sounds like the title of a sci-fi thriller, but it's really just the historical scramble to figure out how to seal a tube of liquid so the outside air can't mess with the data.
Exactly.
And the middle stages of this quest are so scrappy. We didn't just jump from a flawed bowl of water to a modern medical device.
No, science rarely operates in a straight line from a bad idea to a perfect solution. There is always a period of messy trial and error.
The text notes that early pioneers trying to solve this atmospheric pressure problem actually used red wine in sealed glass tubes.
Red wine?
Yeah, they abandoned the open basin of water, sealed the top, and put red wine inside.
I mean, from a purely mechanical standpoint, it makes a lot of sense. You need a liquid to trap inside the sealed environment. Wine expands when heated and contracts when cooled, so it responds to the environment. Furthermore, the deep red color provides high contrast, making it highly visible against the transparent glass background. It was, a practical, readily available material to experiment with.
Well, as creative as the wine was, it was still just a stepping stone. Here's where it gets really interesting, though.
Okay.
The real breakthrough, the one that changed everything, came from a figure the source calls the perfectionist instrument maker.
Ah, yes.
Daniel Gabriel Fahrenheit. He took this sealed tube concept and revolutionized it by introducing what the text calls the silver liquid. He used mercury.
Fahrenheit's introduction of mercury into a perfectly sealed tube was a masterstroke in materials science.
Really? Why is mercury so much better than wine?
Mercury has incredible thermal properties. It expands and contracts with astonishing uniformity across a very wide range of temperatures. Unlike water or wine, it doesn't adhere to or leave a residue on the glass that might distort the reading.
Oh, that makes sense. Wine would leave streaks.
Exactly. And its thermal conductivity means it responds very rapidly to temperature changes. By sealing this highly predictable silver liquid inside a vacuum, Fahrenheit successfully achieved the isolation scientists had been desperate for.
Wow.
The pressure problem was definitively solved.
But Fahrenheit didn't just solve the liquid problem. He gave us a scale. He finally put numbers on the glass. But the source specifically highlights a question that bothers almost everyone who interacts with his system today.
The numbers.
Yes. Why on earth did he use seemingly random numbers, like 32 and 212? For anyone who prefers a simple, intuitive 0 to 100 system, Fahrenheit's scale feels utterly chaotic.
It does feel a bit random today.
32 degrees is freezing. 212 is boiling. Like, if you were designing a system from scratch, those feel like the absolute last numbers you would pick.
It is the great frustration of anyone accustomed to the neat round numbers of the metric system, but those numbers were not pulled out of thin air. Fahrenheit was actually highly methodical.
He was.
Yes, he needed fixed, reproducible reference points to build his scale. For his absolute 0 point, the lowest temperature he could reliably reproduce in his lab, he used a specific mixture of water, ice, and ammonium chloride, which creates a very cold brine. He called that temperature 0.
So his 0 wasn't just really cold weather, it was a specific chemical mixture anyone could recreate.
Exactly. Then he needed a higher reference point. He chose the approximate temperature of the human body, which he initially marked at 96 degrees.
Wait, why 96?
He chose 96 because it is highly divisible. You can easily divide a scale by 2, 4, 8, 12, and so on, which made etching the lines on the glass much easier for an instrument maker.
Oh, that is so clever.
Once he established 0 with the brine and 96 with the human body, the freezing point of pure water naturally fell at 32 degrees on that specific mathematical scale.
No way.
Yes, and if you extrapolate that exact same spacing upward, the boiling point of water naturally lands at 212 degrees.
That completely changes how I view it. It wasn't arbitrary at all. It was based on the physical limits of his laboratory and the need to logically divide physical space on a glass tube.
What's fascinating here is that while the numbers 32 and 200 might feel unintuitive to our modern sensibilities, the actual triumph wasn't the specific digits he chose. The triumph was the rigorous repeatability. Fahrenheit combined his incredibly responsive silver liquid with a sealed environment, and then he applied a fixed, unchanging mathematical scale to it.
So it worked everywhere.
Exactly. Whether he called freezing 0, 32, or 1,000, the profound shift was that a measurement taken in a laboratory in London would mean the exact same thing to a scientist in Paris. Humanity was finally liberated from guessing.
He literally created a universal language for the invisible.
He did.
Once you have a reliable scale and a sealed tube of mercury, you can start mapping the world in a way that was previously impossible. You can write down industrial recipes that work every time. You can conduct chemical experiments that are safe and predictable. We officially transition from feeling to fact.
But as is always the nature of human curiosity, the moment you give scientists a reliable tool for everyday life, they immediately want to find out where it breaks.
Of course they do.
They want to push it to the absolute extremes. Mercury is fantastic for everyday weather, but mercury eventually freezes solid if it gets too cold, and it boils into a gas if it gets too hot.
Right. So we have to move past comfortable room temperatures and start pushing the limits. And the first limit is going down.
Yes.
The source details the search for the absolute bottom, which we know is absolute 0. Once we establish that heat is quantifiable, scientists naturally asked, is there a floor? Is there a point where the numbers simply stop going down?
It is a profound concept. We are so used to the idea that things can always get a little hotter or always get a little colder, but the realization that there is an absolute bottom, a theoretical state where all thermal energy is entirely depleted, changes how we understand physics entirely.
But to measure those kinds of extremes, you run into a massive physical barrier. The source calls this moving beyond the liquid. I want you to imagine trying to measure the temperature of a star, or like a modern industrial blast furnace melting steel with a glass mercury thermometer.
It would be comical.
It would. The glass would instantly shatter, the liquid would vaporize, and you'd be left with nothing. So what does this all mean? How do we measure temperatures that completely destroy our traditional instruments? The source mentions we started using metal and light.
If we connect this to the bigger picture, moving beyond liquid was the only way we could start measuring the extreme environments of the universe.
Okay.
When a physical liquid in a glass tube fails, you have to look for other physical properties of matter that predictably change with heat. Certain metals, for example, alter their electrical resistance as their temperature changes.
Okay, I think I get the metals part. The heat messes with the physical wires.
Yeah.
Because heat is just kinetic energy. Getting the metal hotter means its atoms are vibrating more violently.
Exactly.
If you're trying to pass an electrical current through that wire, those traveling electrons are suddenly navigating an obstacle course of violently shaking atoms. More heat means more resistance. So we just measure the resistance to figure out the temperature.
That is the exact mechanism. By measuring the precise change in electrical resistance, you can reverse engineer the temperature of an environment that would obliterate a traditional thermometer.
Wow.
That allows you to measure the inside of a jet engine or a high-temperature kiln.
But when we talk about measuring stars, we can't exactly run a copper wire to Alpha Centauri.
No, we cannot.
The source talks about using light. Are you saying the extreme heat is actually changing the physical properties of the light traveling to us across space?
It is dictating the properties of that light at the exact moment of emission. This brings us back to that kinetic energy you mentioned earlier.
Right.
As objects get incredibly hot, their atoms jiggle with immense ferocity. This violent motion causes them to release energetic photons. You've seen this on a smaller scale if you've ever watched a piece of iron being forged by a blacksmith.
Oh yeah, when it glows.
Exactly. As the iron heats up, it begins to glow a sluggish, deep red. As it gets even hotter, the atoms move faster, emitting higher energy photons, and the color shifts to yellow, and eventually to a blinding high-energy white or blue-white.
So the color is quite literally a direct translation of the temperature.
Precisely. By analyzing the specific spectrum of light, an object emits a process called spectroscopy. We can determine its exact temperature from millions of light years away. We don't need to physically touch the star. We just have to read the light it throws out into the void.
And it's staggering. We went from a doctor holding a weather-dependent tube of wire, trying to guess a fever, to literally reading the light of distant galaxies to know how hot they are.
It's an incredible leap in capability.
And it leads directly into another crucial concept from the curriculum, which is calorimetry. The source describes it as the science of measuring heat itself.
It is a subtle but incredibly important distinction in the world of physics. Measuring temperature and measuring heat are not the same thing.
Wait, so temperature is like the speedometer, but heat is the weight of the car. Let me see if I have this right.
Go for it.
A tiny toy car hitting you at 10 miles per hour is nothing. It just bounces off your shin. But a massive freight train hitting you at 10 miles per hour is utterly devastating.
Right.
The speed or the temperature is exactly the same, but the total kinetic energy, the heat, is vastly different.
That is a phenomenal analogy. Temperature is a measurement of intensity, the average speed of the particles. Heat, in the realm of calorimetry, is about the total amount of energy transferred.
Okay, that makes sense.
Think of a 4th of July sparkler. It burns at a very high temperature, maybe 2,000 degrees Fahrenheit. The particles are moving incredibly fast.
Yeah.
But the total mass of the spark is so small that it contains very little total heat energy. That is why a single spark landing on your skin might sting for a second, but it won't instantly boil the water in your cells. Calorimetry is about quantifying that total energy payload.
So temperature is the intensity, but heat is the actual amount of energy doing the heavy lifting.
And understanding how to calculate that total energy payload is what allowed the Industrial Revolution to happen.
Oh, wow.
It allowed us to truly harness heat to boil massive vats of water, power steam engines, forge steel, and essentially build the modern world. It is what the source brilliantly refers to as the legacy of the jiggle.
The legacy of the jiggle. I love that phrase. It sounds like a forgotten 1970s dance craze, but it is actually the fundamental truth of thermodynamics.
It perfectly demystifies what heat actually is at a microscopic level.
Because throughout this deep dive, we've talked about heat as this invisible force. But the legacy of the jiggle frames temperature not just as a feeling of hot or cold, but as a direct measurement of invisible motion.
Exactly.
It is the kinetic energy of atoms and molecules bouncing around. The faster they move, the faster they jiggle, the higher the temperature. When things cool down, the jiggle slows down.
Right.
And when we talked about absolute zero earlier, that absolute bottom of the scale, that is simply the theoretical point where the jiggle stops completely. Everything is perfectly, entirely still.
And that realization that temperature is just motion is the ultimate destination of our 400-year journey. We stopped trying to measure a mysterious, invisible quality and realized we were simply measuring movement.
It totally